For this circuit activity, we're going to take a look at some very simple circuits using batteries, light bulbs, and measure the voltage and the current as you add and remove different components. You had already built some simple circuits in class, but we hadn't gotten to taking measurements, so this is the measurement part. So to make this happen, we're going to need our digital multimeters. We will need a series of D-cell batteries, 1.5 volts, some light bulbs, and some wires attached to alligator clips to complete our circuit. So let's begin. The first thing we're going to do is just make a very basic circuit with a light bulb and a battery. So what I'm going to do is I'm going to take my battery, attach one end of the battery to one end of the socket for the light bulb, and attach the other end of the socket for the light bulb to the other end of the battery. And as you can see, the light bulb glows a little bit. It's not that bright, but if you take a look at that, you can see that it is in fact glowing. And if I disconnect it, it goes away. Okay. So the first thing I'm going to do is measure voltage. What I will do is I'll turn on my multimeter, and I want it set to DCV, which stands for direct current voltage, which is what we get from a battery. And if I go ahead and touch this to either end of the battery, okay, I get about 1.47 volts. So this battery is pretty much at full capacity. It's a 1.5 volt battery, so looks like we still have all of the energy left inside of it. If I go ahead and take a look at the voltage for the light bulb, what it is doing is it's giving me a value that's somewhat close to 1.5, but it's a negative value. And what this negative value indicates is that the energy that comes from the battery voltage is being used up by the light bulb. So a positive voltage indicates that energy is being given. A negative voltage indicates that energy is being used up. And in this case, we can tell energy is being used up because the light bulb is lit. Now, that value is not exactly the same as the value, it's not the negative value of the value of the batteries. It's different by about 0.17 amp, or 1.7 volts. So if we take a look at the wires themselves, okay, so I'm going to touch both ends of the wires here. Okay, and as you can see, there is a little bit of value from the wire themselves. So a little bit of the energy comes up, gets used up by the wires. If we go to the other side of the wires here, okay, we see that a little more gets used up as it goes from the light bulb back to the battery. So we'll explain later on why that's the case, but most of the energy is lost from the light bulb. Some of the energy is lost in the wires, and then the purpose of the battery is to give energy to those electrons so they can keep moving through the battery, and then they can move through the wire. Next, what we're going to measure is the current. And in order to measure current in a circuit, you actually have to put your measuring device, which in this case is our digital multimeter, into the circuit. We can't just touch 2 points on the circuit and measure it. So what we have to do is we do have to disconnect our circuit. Okay, and now the light bulb goes out. And what I'm going to do is I'm going to put one end touching the battery and the other end clipped onto this other alligator clip. But before we do that, we do have to change our multimeter in a couple ways. Number one, what we have to do is switch it from DCV, direct current voltage, to direct current A for direct current amps. And then I'm going to go ahead and set that to a maximum of 200 milliamps. Okay. So what I'm going to do is one end is going to be clipped on to the probe, and then in order to complete the circuit, I'm going to touch the battery. So now the current will go from the battery through the multimeter and through the light bulb and back into the battery. So I'm now closing the circuit. And you can see we have a reading of about 186 milliamps. So a milliamp is 1/1000th of an amp. So this would be 0.186 amps. And then when I disconnect it, it goes to 0. And if we take a look at the current reading, if we attach it on the other side of the battery, we get nearly the same current. I got 185 milliamps. Okay, so the current is almost exactly the same on both sides of the battery. Now let's take a look at what happens to the current and the voltage when we put another light bulb in with one battery. So I'm going to go ahead and unplug or unclip the alligator clip from the battery. I'm going to go ahead and attach another light bulb, and then I'm going to go ahead and attach the battery to the new light bulb. Okay. And it's really hard to see what's going on, so I'm going to go ahead and turn off the overhead light so that you can see what's going on. It may be hard to tell in the video, but both light bulbs are very dim right now, and I'll confirm that to you. I'll move it up really close. When it's clipped on, there's that little faint glow from the filament, and when I detach that, that faint glow goes away. And I'll show you the same thing for the first light bulb. Very faint glow in the filament, and then it goes away. I'm going to put the lights back on so we can read our digital multimeter, but I just want to confirm to you that the fact that the light bulbs are lit, just very dimly. So let's go ahead and measure voltage. Change my multimeter to read DCV, direct current voltage. And if we take a look at the battery, okay, the battery's still reading 1.47 volts. And then if we go and look at the light bulb, okay, it's reading negative 0.64 volts. So even if we couldn't tell that the light bulb was lit because it's so dim, we can tell that energy is still being used up, and this is a completed circuit because there is this negative voltage indicating that the light bulb is using energy. If we go ahead and look at the second light bulb, okay, we also have a negative voltage, about the same value, indicating that the light bulb is using up energy from the circuit. And then those two values, they were both about negative 0.66, which doesn't add up to the positive value of the voltage. And once again, if we take a look at our wires, there appear to be a little bit of energy loss happening in the wires. So a little bit there, a little bit there, and a little bit there too. Now let's measure current. I'm going to change the setting here to measure DCA, direct current amps. And we do have to make our multimeter part of the circuit. Okay. And if we take a look, our current is a little bit lower than it was when we had just one light bulb. Let's see if the current is any different in between the two light bulbs. So the first current I was measuring there was from the battery to the first light bulb. Let's go ahead and try this. Okay. Pretty close to the 150 we had before. Those are milliamps, by the way, so that's 0.15 or 0.150. And then if we go ahead and take a look at this third one here, or this other connection from wire to light bulb, it's very close to 150 milliamps. And if we look at the other end of the battery, we have a current that's very close to 150 milliamps. So the current really doesn't significantly change throughout the circuit. The current is lower than when we had one light bulb, but with the two light bulbs throughout the entire circuit, the current doesn't really change. Let's go ahead and do the same set of measurements, but this time let's do two batteries. So this will give us more battery voltage, and we'll see how that influences the voltage and the current. So what I'll do is I'll disconnect my circuit, clip my two batteries together. They're both 1.5 volts, so we should be getting something around 3 volts. And if I go ahead and do that, the light bulb is shining a lot brighter than it was before. And let's go ahead and measure the voltage and the current again. I'm going to change my multimeter back to DCV so that it actually measures voltage. And if I take a look at my voltage reading when I touch both sides of the battery, I'm getting about 2.6 volts. Okay? So the new battery I added has a little bit less energy left than the first one. And then if we take a look at the measurements we were doing before, if I take a look at the voltage change across the light bulb, okay, it has a big negative voltage indicating that energy is being used up by the light bulb. And you can see the number is dancing around a little bit. That's because I'm not maintaining good contact between the probes and the light bulb. So now it's stable again. And then same thing as before, if we take a look at that voltage from the battery, that negative voltage from the battery doesn't exactly equal the positive voltage from the negative voltage from the light bulb doesn't exactly equal the positive voltage from the batteries. And the reason is we're going to have a little bit of change in voltage as we go through the wires. So that's negative 0.02. And then if we take a look at the other side of that, it's negative 0.06. Okay? So once again, we're losing energy in the wires, and then the electrons will go into the battery, pick up a little bit of energy to help them move through the battery and then move out of the circuit, and then they continue going through the circuit again and again and again and again and again. To take a look at current, we once again have to open up the circuit and put our multimeter through this. Okay? So I'm going to go ahead and change my reading here to DCA, direct current amps, and I'll go ahead and I'll connect one end to the circuit and the other end to the battery. Okay, and what happened here is this is just showing a 1 there. This indicates that the current is too high for the multimeter to measure in this mode. So clearly we have an effect here where putting another battery in increases the current. So there is a setting on the multimeter to read more current. I have to do two things. First of all, I have to twist it to this 10 amp reading, and then we have to plug this probe into this spot here, and it says 10 ADC, so it can handle a current up to 10 amps, and we're going to need that for this circuit since we added more voltage. I will go ahead now and touch the other end of the battery, and we're reading 0.26, and this is in amps now. So this would be 260 milliamps what we were measuring before. So the current has increased by adding another battery in there. And if we take a look at the current on the other side, okay, we'll see we get the same exact reading here. So the current doesn't change on either side of the light bulb or either side of the battery. Finally, for this setup, let's take a look what happens when we add a second battery. So I'm going to disconnect my circuit and clip my batteries together. And you'll notice that the light bulbs are glowing a little bit brighter. It's still kind of dim, but they are clearly lit, as opposed to last time where it was kind of hard to tell unless we had them up really close. So I don't even need to turn the lights out for this one. Once again, let's measure voltages and currents at everything going on in this circuit. So I'm going to go ahead and change my measurement to volts. And I'm going to go ahead and take a look at voltage. Okay, the battery voltage is about the same as what it was before when we had the two batteries, about 2.6, 2.67 in this case. And then let's go ahead and measure the change in voltage as we go through the light bulbs. This one's about negative 1.16, so that indicates that the light bulb is using up more energy than it was before. And we can tell because the light is brighter than it was with just the one battery. And then if we go ahead and take a look at the other light bulb, it's using up about the same amount of energy. Its reading is negative 1.19 volts, indicating that the light bulb is in fact using up the energy of the circuit. Okay. If you add up those two values, once again, the negative total there doesn't equal the positive total from the battery. And once again, the reason for that is that the wires themselves do account for some of the energy loss. Finally, let's measure current. As we had to do before, we do have to disconnect the circuit and put the wire so that the current goes through the multimeter. And we're at 191.7 milliamps. Let's take a look at some other parts of the circuit. $190 exactly after the first light bulb. $193.998, still going down after the second light bulb. And if we take a look at the other end of the battery, let's see what we get. It's dancing around 192, 193 milliamps. And so as you can see, the current, once again, doesn't significantly change at any point in the circuit. I do want to emphasize one more point about the circuit. You do need the circuit to be fully connected at all points. The lights went out when I disconnected parts of the circuit to take the measurement, but any part of the circuit that is disconnected makes it an open circuit and current no longer flows and we can't take any measurements. For example, you can see both of these light bulbs are lit. If I go ahead and detach the batteries, the light bulbs go out. I could disconnect this second light bulb, and as you can see, the other light bulb went out. So these are disconnecting parts of the circuit and preventing current from flowing through, so we can't take any measurements there. We had mentioned before that there appears to be some energy loss to the wires, and we want to look at why that's the case. It's kind of odd because copper, most wires are made of copper. Copper is a very good conductor, so it does easily and readily promote the flow of charges. And what this is this is a property of all electrical materials called resistance. As the name implies, it resists the flow of anything, charged particles or not. And it has to do with the fact that there are atoms that are in the way. Copper is made up of atoms, and so these electrons, as they're flowing through the circuit, bump into these atoms. And so the more bumping into there is, the more the resistance is. And you can actually measure the resistance of things using our digital multimeters. There is a setting here with the Greek letter omega, and that is the symbol for resistance. So let's go ahead and take a look and see if we can get a resistance measurement on these wires. Okay. So if I go ahead and clip both ends of these, okay, we do get a reading of about 1.9, indicating that the wires themselves do have some resistance. So anytime you have resistance in a circuit, there will be some energy lost that the battery is supplying. We also have specific devices that we put into a circuit to create resistance. So we can't really control battery voltages. Those come in pretty standard values. And the voltage you get from the wall that you plug in devices is 120 volts. And it's just a lot easier just to have a set voltage than to have different voltages for different houses or even different parts of their house. So you can put resistors into circuits. So I have a couple versions here. This is just a ceramic resistor used for physics labs. So if we go ahead and measure, okay, this is measuring a resistance of about 16.4. This little number here next to the omega indicates that it should be about 15 ohms. So there is a margin of error for these devices here. But as you can see, this has a resistance value. If I take this other resistor here, okay, this has a 25 ohms here, so that should have a higher resistance. And so we should have a value close to 25 when we measure the resistance, so 26.5, okay? Let's take a look and see what happens to a circuit when I put a resistor in it. I can't tell just by looking at it whether or not the resistor is doing anything because it doesn't light up. But if I let this run for a while, I will feel that the resistor does get hotter as current flows through this. But let's go ahead and take a look at these measurements for voltage and current when I put a 25 ohm resistor into the circuit. So if I take a look at voltage, okay, you get a voltage of about 2.8. And then if I look at the change in voltage across the resistor, okay, pretty much all the voltage in this case is being lost by the resistor. So, and it's not like it's lighting up like a light bulb. Its sole purpose of the resistor is just to restrict the flow of current and to create an energy loss. So we're losing a lot of energy from the battery through this resistor. Let's go ahead and take a look at current. So we'll go ahead and change this to DCA. If I take a look here, we're just a little bit over 100, and that is the lowest current we've had compared to any of the currents with the light bulb. So this is just restricting the current. And that's its sole purpose. It's just to restrict currents and lose energy. And there's a lot of purposes for this in a circuit. But you can see what the resistor does in terms of regulating current in a system.